So, an important thing which I have to show you is that this mean reflection map that we saw is a valid unitary operation. Right. So, this is important to establish this. So, what we will show is that this map is equivalent to this circuit. So, we will prove that this map is equivalent to this circuit, okay, and then using that it will follow that this is unitary. So, let us see how this works. So, if I if I call, let us see. So, if I have 2 Hn 0 yeah. Okay. So, let us study this map. Okay. So, I am going to call this as psi. This is our favorite state, the superposition over all possible inputs. Okay. So, we are analyzing this state that we have. So, now let us see what we get when we apply this map to some arbitrary state. Okay. So, consider an arbitrary state summation alpha xx, and now I am applying this map, right. So, what do I get? I get 2 psi summation alpha x inner product of psi and x, right, minus summation x alpha xx. Everyone agrees? Okay. So, this is just simple algebra. So, very good. So, now let us study this term over here. Can anyone tell me how does this relate to that to mu? How does this relate to mu? Can you tell me? So, remember what was mu. So, mu was summation over all x alpha x over 2 to the n by 2. No, sorry, over 2 to the n, in fact, right, that was mu. Now, can you tell me what is this? So, I claim that this term with the with the curly under brace, I claim that this gives me summation x alpha x, right, divided by 2 to the n by n over 2. So, it just follows from the definition of psi, right, and the inner product, what about the inner product? Exactly. So it will just be 1, right? So this is what I get. So in particular, what is this going to be? This is mu times 2 to the n over 2, right? So let's continue. So basically here I get 2 times summation over all x, 1 over 2 to the n over 2 x mu times 2 to the n over 2 minus summation alpha x. Does everyone agree? So I am just substituting, sorry. Does everyone agree? So I am just rewriting. So I wrote you know, psi as this, correct? And I wrote this term as this. So now let's look at what we got. So we got 2 times, sorry, wait, yeah, good. So we got 2 times mu minus summation alpha x, the whole times x. Does everyone agree? I claim that I got summation over x 2 times mu minus alpha x. Everyone agrees with that? Okay, and this is exactly the map that I wanted to apply in the algorithm. Okay, so this shows that this map is indeed a valid unitary. Okay, so this is the map that we applied. Any questions? So now that we have seen you know, at least the algorithm and sort of some high level of the analysis, let's try to understand you know, in a more intuitive way what is happening. So first of all, let's recap the algorithm. You know, I prepare the superposition and then I sort of apply the function, right? I reflect about the mean, again I apply the function, I reflect about the mean, I apply the function and reflect, and so on and so forth, and finally I measure. So first of all, note that you know, this is also falling within our theme of rotate, compute, rotate, right? Because if I look at this loop, this loop is actually doing compute and rotate. Why is you know, this mean inversion? So the first step is anyway a compute step, right? So I am applying this function. The second step is this reflection about the mean. Notice that what we showed now, right, is that basically this reflection about the mean is nothing but Hadamard times this sort of simple matrix times Hadamard again. Okay, so this is like a so you see how the QFT is again coming into the picture. So remember that the Hadamard is what is implementing our QFT as we saw last time, right? So now you can see this algorithm also from that point of view. So basically we started by getting the uniform superposition of input. So this is, you know, a rotate, right? And then in a loop we do compute, rotate, compute, rotate. So it's very clever, right? I mean, basically as long as one point alone satisfies this criteria, it's really using the phase kickback trick to sort of flip that one point alone, right? And now once we flip that point, now see, you're applying such a clever way to ensure that all but the non-special points remain more or less where they are, right? And this special point alone keeps increasing in magnitude. So by doing this repeatedly, we are hoping that we will get this amplitude to be constant, and once it is constant we can measure, and then that means that we will get this point with a constant probability, right. This is the main idea. So now that I showed you the main idea of the algorithm, I'd like to ask you, what do you think can go wrong in the picture that I showed you? What do you think can go wrong? So why are we not done yet? So see, actually we were just a little bit imprecise. Let me make it just a little bit better. So instead of 3 mu, see, because mu is shifting around, right. So let us call this 3 over 2 to the n over 2, right, and then the next step it will be 5 and so on. Okay. So my question to you is the following. So what can I really claim that in every step it's going to keep increasing? So can this process go on indefinitely? Is there an upper bound on this or no? So that is one of the problems, right? So basically I cannot really claim sort of so carelessly that this is going to keep increasing. So does it really can it go beyond 1, for instance? It cannot, right. And then moreover, now what happens if it grows so much that it actually completely changes the mean, right? In that case, what can go wrong? Yeah, so when the amplitude on x star is very high, okay, and I do this flip, right. So this could mean that there is one negative amplitude which is so high that the whole mean came down so much, right, that now maybe the when I do this flip further, it could mean that in fact the amplitude on my special point is now decreasing, isn't it? Do you see that? Because if my mean is negative, let us say, suppose the amplitude on x star is so large and negative that the whole mean became negative, then what will happen is that the amplitude on x star will now start decreasing, isn't it? So then I'm not making any progress at all. So I wanted to talk about these points because see, first there is like a very clever idea, this idea, right, that I mean I think it's a really surprising and cool idea, right. Like basically it's so clever, like this flipping this one point and then setting up a unitary transformation which seems to leave the other points unaffected but kind of keeps on magnifying this difference, right. So you are trying to sort of push down the other points and increase the amplitude of this point alone. So the probability of getting this point should become higher and higher. But I wanted to emphasize that this is all well and good as an intuition, but in order to make this work out, you need to do a careful analysis. Okay. So let's start doing this analysis. Okay, so let's look at it more carefully. So let's introduce some notation. So let me write this. Okay, so more careful analysis. Okay, so let me introduce a little bit of notation. Let alpha t be the amplitude of x star after the tth step okay, where one step consists of applying OF followed by this reflection step. This is also called the Grover diffusion gate. Okay, so this is just some notation. Now let beta t be the amplitude of any other point at the same moment. And let mu t be the mean of all amplitudes after the oracle gate on the teeth step. So note that mu t is not after the entire teeth step, it is only after the oracle gate. So basically when the amplitude on x star is negative, at that point you are computing mu t. So can you tell me what should mu t be using alpha t and beta t? So let us call, okay, so let n denote 2 to the n. So now can you tell me what is mu t? N minus 1 beta t plus, it is minus, right, because I did not, this is after the oracle gate, so it is still negative. So minus alpha t the whole by n, right, everyone agrees? Okay, good. So good. So now we have to prove two things actually. One is that there is a good increase if if I am in the early stages, intuitively speaking, and then I have to also prove that the increase is not so much that I run into the issue that we discussed earlier. Okay, so let us write these propositions. So the first proposition is that suppose alpha t is less than equal to a half, okay, and n is greater than equal to 4. Okay, so remember that capital N is 2 to the small n. Then we claim that alpha t plus 1 is greater than equal to alpha t plus 1 over square root n. So this is sort of what we were seeing in our nice picture, right, that basically when I do this I get a 1 over square root n increase. So note that if what is this proposition really saying? So if alpha t is not already too large, so let us give it a bound. So if alpha t is less than half, let us say, okay, and I also want my n to be somewhat big. So in particular let us at least say that capital N is at least 4, we will see where that comes up in the proof. In that case I want to claim that alpha t plus 1, right, is so the mean on my special point, or the amplitude, I am sorry, the amplitude on my special point is at least the old amplitude plus 1 over root n, and this is what we were seeing geometrically, right. Is it fine? Yeah, okay. So okay, we will prove this. Okay, fine. Let's prove this first. I was wondering if I should show you the second proposition first, but that's fine. So let's prove this proposition. Okay, so let's prove it. So first, because the sum of squares of all amplitudes is 1, I can write that alpha t the whole squared plus n minus 1 beta t the whole squared is equal to 1. Okay. So this gives me that 1 is less than 1/4 because I assumed that alpha t is less than half. Okay. So this is 1/4 plus n minus 1 beta t the whole squared. Okay, this is just some simple thing. Now by rearranging, which I will not do, we can get that beta t is greater than equal to square root 3 over 4 n minus 1. It's obvious, right, how you get this? Okay, good. So we got this. So now let us look at what happens to mu t. Okay, so therefore mu t, which we said is minus alpha t plus n minus 1 beta t the whole over n, we said it's this, right. So by using the bounds that we got, so alpha t we anyway said is less than equal to half, right. So minus alpha t will be greater than equal to minus half. Okay. So I will get minus half plus n minus 1 square root 3 over 4 n minus 1 over here. Okay, the whole over n. So this is just substituting the two bounds that I have. Okay, fine. Okay. So now this is in fact equal to half n minus 1 square root 3 over n minus 1 minus 1, right, the whole over n. So I know that, I mean, from the previous page you cannot see, but it's just simple stuff. Okay, so you can check it. So this will be half square root 3n minus 3 minus 1 the whole over n. Okay. Is it fine? So this n minus 1 will cancel and you will get one n minus 1 inside the square root. Okay, and this is going to be equal to half 1 over square root n when n is greater than equal to 4. So this implies that alpha t plus 1, which is 2 mu t plus alpha t, is greater than equal to 1 over square root n plus alpha t, which is what we wanted. Okay, so we are saying that as long as your alpha t is sort of not already huge, it's bounded above by half, right, I will get in my next step at least a 1 over square root n increase. Okay, so that is good. So this is showing that at least I am making progress, right. So this is not just hand wavy, but we are proving that we are making progress.